Okay, starting the recording officially speaking then. All right, can everyone hear me, see the orange webpage? Excellent. So I wanted to draw your attention to, since I didn't get to remind you on Tuesday, what you can be working on if you haven't submitted already, which is your Homework 5 plan document is due Monday. This has been up for about a month or so, but you may not have paid attention to it until now. That's fine. The main point of this is for Homework 5, you are going to be doing analyses using generalized linear models on data you care about, or publicly available data if you don't have any data you care about handy. And I want to give you a sense to, for me, I want to be able to weigh in on your plans. That's the idea. So this is worth 2 points. It's just an outline where I'm asking you some questions that you can insert directly into this Word document. What's your study about? What are the variables? What are you planning to do? And then I can give you feedback. And so I will put together a rubric for what Homework 5 is going to be once I get a chance to read through these. That way I can make sure that I've covered all of the situations that you're likely to encounter. So please let me know if you're not sure what you should be doing, or if you're not sure if your idea is going to work. I would encourage you to pick a model that we've already covered. So that would be including binary, categorical, either ordinal or nominal, and counts. And then this week we'll be starting, into next week we'll be starting proportions. So rates or amounts, percent corrects, those kinds of things would also be fair game. So any questions on that outline that's due Monday? If not, let me or the TAs know. We're happy to talk with you about that. And then the next thing you'll have to do, which is not yet available, but I'm going to put it up either right after class if I get a chance, or on tomorrow morning at the latest, is Homework 4, which is going to be about counts. So this one is going to be more challenging on the predictor side and less challenging on the outcome side. So Homework 3 was challenging to try to figure out exactly what the submodels are predicting. In this case, it's going to be straightforward. It's going to be using a log length the whole time and a count distribution of some kind, but it's going to have some interaction terms and some different kinds of interaction terms than what you've seen. So I want you to be able to start that as soon as you're able. I will let you know when that's available. It will be due Monday the 8th. And then we're winding up. So then we have another formative assessment, Homework 5, and then your last Homework 6 is due at the end of finals week. So we're getting there. I'd say it's too early to start a countdown just yet, but we're closing in on the point where we can start counting the weeks. That's April is a good measure of that. So any questions? Good going on? All right, then I'll shut that off. And we were talking last week about counts. Remember counts? What kind of link do we need for counts? We'll start with the softball questions. Yeah. And feel free to type, and if someone already typed your answer, go ahead and type it anyway, because I like to see as many people participating as possible. Yeah, log, the natural log in particular, not log base 10 or some other kind of log. And we need logs to make sure that the predicted counts stay positive. So we're reeling in the lower side, letting the upper side go to whatever it wants to. So that means in terms of the type of relationship that's being fitted between an outcome and a predictor, it's not going to be a straight line in predicting the raw count. It's going to be a bendy line that's like an exponential kind of curve. So a linear relationship in the log scale translates into a nonlinear relationship in the data scale, the same as it did in Logitland. And in counts, we have to worry about zeros. That's what we were talking about, I think, before, right? We can have counts that don't have zeros, in which case we need a zero truncated distribution to go with that, either Poisson or negative binomial usually. Negative binomial being the stretchy version that allows for overdispersion, variance exceeding the mean in a quadratic fashion. If we have too many zeros, I think this is where we ended up last time, is options for dealing with too many zeros. Does that sound right? Am I forgetting anything? I'm imperfect. It's quite possible. No, too many zeros? All right, now let's do this picture. I like this picture. This is slide 17 in example 3. I stole this picture out of a 2007 tutorial on how to use count models within the context of family psychology. The example that they are using is on the x-axis is steps taken towards divorce, and these are the histogram of the sample. And overlaid on this histogram are the fits to 4 different kinds of distributions. So Poisson and negative binomial are the ones that fit the worst. They're the ones that start right here, and they expect more mass within this middle area here than what the data suggests. To fix it, they have overlaid 2 alternative distributions, which is zero inflated Poisson or zero inflated negative binomial, in which you just basically add in the extra amount of zeros so that the model perfectly accounts for the actual number of zeros. So some of the zeros are what are known as expected, and some of them are unexpected or structural zeros is the terminology that goes with that. So in terms of the submodels that would go with that, let's go to back a slide. This is slide 14 instead. To do a zero inflated model, you're actually fitting 2 models at the same time. So this is the same idea as submodels as we had in categorical data, where there's 2 different versions of y being predicted. The critical thing with these models is that 0 is part of both of them. So your traditional count model, which is an example of which is given here, is predicting the log of the expected count from some kind of linear predictor as usual, but the outcome includes the zeros. So theoretically, what you are predicting is the expected number of zeros within a traditional count distribution, either negative binomial or Poisson. The second submodel then is focusing on the probability, predicted in logits usually, of being an extra zero or a structural zero, meaning somebody from an alternative population that would never do this behavior in question, and that's why they're a zero. Like they could never be anything other than a zero. That's the idea. That explanation falls apart real quick in multi-level settings or in longitudinal settings, in which case you might have somebody have probabilities of being an extra zero that move across time. Like you're not always an extra zero, which is where that explanation falls apart. But for cross-sectional data, it seems reasonable. So then what you are predicting in here is a binary outcome, whether or not you are an extra zero. And because that's a binary distinction, we would use a logit or a probit in most cases to predict that probability. So you can have a separate submodel that has predictors in it if you want. They can be the same predictors as in this model, or they can be different ones, or you can just have an intercept. The purpose of just having an intercept would be to ask the question, well, what is the probability of being an extra zero in the first place? If that's a really tiny number, then we probably don't need a zero inflated submodel. Like there are no extra zeros. So in terms of the example that we did, we looked through this possibility because it looked like we may have had some zero inflation. So I fit a model that had zero inflated Poisson, and the logit of being an extra zero was actually quite high. It was an intercept of minus 0.55 in logits, which corresponded to a probability of 0.37. However, Poisson distribution didn't fit that well in the first place. When I tried to do it with a negative binomial and add a zero inflation factor, Stata threw up. R was able to give me something, but it turned out to be a logit of minus 11, which translates into a probability that is very, very close to 0. So the conclusion would be, okay, if the probability of being an extra zero is basically 0, I don't have zero inflation. I don't need to add anything extra to the model. And I didn't do examples of the other alternative hurdle version because it didn't make sense for this type of outcome. So I think that was where we had gotten to, and then I had showed you count fit to decide amongst these things. So in terms of what would be reasonable to compare, like you can think of these as like a 2x2 grid, where you have distribution type and then whether or not it's zero inflated. So like Poisson not inflated is the simplest one, and then negative binomial and zero inflation is the most complex. So you might want to compare like across the rows or across the columns. Is negative binomial better than Poisson? Like, is there overdispersion relative to what the model says? And then within the types, like, do we need zero inflation at all? So Poisson no inflation is nested within all the combinations. The most complex is negative binomial with inflation. So you can sort of work your way around the grid to do comparisons to figure out what you need. And count fit within Stata is a routine that I found that does that. There may be parallel routines I'm not privy to in R. But this one does the comparisons for you in terms of likelihood ratio tests, comparisons of AIC and BIC, and then also it used to do something called a Wong test, which is it's a very different way of comparing models, but I read the documentation and they don't think this is right anymore, so they quit spitting it out. So that's why it has dots there where there used to be output. So I'm not going to talk about that one because it seems that people are not really sure when you're supposed to be able to use it. But everything is pointing to the idea that negative binomial without overdispersion is enough for these data in this particular case. And it also shows a plot of the original outcome on the y-axis and the predicted outcome on the x-axis in terms of the discrepancy between observed and predicted. So 0 is what you want, and it has the predicted number of counts at each point on the outcome. And it looks like the red line is the closest to 0 across the board. So negative binomial is good enough, and she wrote it up and turned it in. Okay. So let me take a survey. Who finds this idea of extra 0 really confusing? Can you get any votes for that? I do. Like if somebody is a 0 in your data set, like how are you possibly going to explain to your readers what an extra 0 is versus an expected 0? Like it's just 0, dude. They don't come in flavors. Like 0 is 0. There's not like 0 light or 0 diet or 0 regular, right? It's just 0. So if you're like, what does that mean? Let me show you a different way of thinking about it, which is hurdles. So this is slide 16 that I had skipped over because it's not in the picture. Hurdles is enough with this expected 0 nonsense. I'm going to divide this up into a model that predicts if and how many. That's what I name these things as. So a hurdle model has a submodel to first differentiate, excuse me, I'll go in the order here. The hurdle model takes the count part and takes off the zeros. It says, among people who are greater than 0, what is the predicted count? Like if you are in the population where this is relevant, right? You could have a 1 or a 2 or a 3 or whatever. How do I predict what you have? And then you can put your linear predictor on that for your expected count. Now, because this distribution does not have zeros in it, standard Poisson and negative binomial are not going to work. So we need the 0 altered or 0 truncated versions of those. So the same solution that works when you don't have zeros in the first place is applied here. 0 truncated or 0 altered is what those are called. Those are count distributions without zeros. So that part, you're just predicting how much. In then the second submodel is predicting whether or not you're a 0 or something else. All the zeros. So in this case, you're predicting the logit of being any 0 as opposed to extra 0, which is the 0 inflated models. So this is the if part, right? Are you part of this? Like, do you have this tendency or are you part of this population? If. And then if so, the people who are in it get this model. So to me, this is a lot easier to explain because you're predicting whether or not you have a count and then how much if you do. This doesn't lend itself to all kinds of outcomes, however, which is why I don't have an example for it. But I can give you some examples that I've seen. The problem is that the amount part doesn't necessarily correspond to a count distribution. So this idea of a hurdle, excuse me, so in the next unit, I'm skipping ahead a little bit because I know where we're going. So I'm foreshadowing. In the next unit, when we have continuous outcomes that are skewed, this same idea of hurdle is going to be called two-part. And it's the same thing. Like, do you have a 0 or not? That's one. And if not, what do you have? Two-part. So I've seen this in a couple different contexts. So for instance, in my master's thesis and dissertation, I was measuring response time to a task where people only had so long to complete it. And if they didn't solve it within that time, then the item disappeared and they were on to the next one. So in that case, I have accuracy and response time potentially. Like, did you find, so they had to search through something and find something. Like, did you find it? Yes or no, right? That's one submodel. And then if you found it, how long did it take you? That way you can use cases in which someone doesn't have a response time. Similarly, if you had like psycholinguistic kinds of outcomes where your response time to say if something's a word or not a word, something like that, then you can say, did you get it right? And if so, how long did it take you? Traditionally, items that are not correct are thrown out of the analysis because you're not sure what the process is, but this way you could keep all your data. As another type of example, there was a task that one of my former graduate students worked on for his master's thesis looking at impulsivity in adolescence. And it was a task where they were in a pretend car and they were driving to a party and they were told to get to the party as fast as they could. But then in the course, there were stoplights that they had to negotiate while driving. And the stoplights were designed to turn yellow just as they were approaching an intersection, and they had to decide whether they were going to floor it and go through or stop like a responsible human being. So then the outcome was, how long did it take them to stop? Like there was a response time from when it appeared to when they hit the brake in their pretend car. Well, guess what happened? Not everybody stops, right? So if somebody decides to floor it through the intersection, you don't have a latency measure. Well, that's not missing data. Like that's literally the point of the task, is to measure this kind of decision making. So in that case, I helped a student come up with, it was a measurement model, but it's the same principle of, did they decide to stop or not as one outcome? That's one submodel for each item. And then if they did decide to stop, how long did it take them to make that decision? And it turned out that the stop or not was the thing that was related to the other variables that he was interested in, not how long it took them once they decided to stop. So they would have missed out on a big part of the story had they just thrown out the trials in which they didn't have a latency. So I feel like this kind of hurdle model is very useful in practice when there's a qualitative difference that would lead someone to have like a 0 versus something else. I don't know if you can think of any other examples from your worlds that would go along with this, and TAs, you can help me out too. Can you think of anything that falls into this kind of two-part category? Those are the ones that I came up with. No, fair enough. I put you on the spot. But the idea is that this is a hurdle model, and when it's in counts, it's called a two-part if the amount part is continuous instead. So, excuse me. And you can find this in various places. I've listed the ones that I've found. I found this was funny. In Stata, it's called churtle. I don't know what the C stands for, maybe count or something, but that's what I say. It's churtle. Making it up. And the most unpronounceable acronym ever, yeah, ZTPNM. So, Vladimir, you raised your hand. There you are.
I think that I have a quick example
Great.
related to admission, the
Okay.
project that I show you this semester.
Mm-hmm.
If our dependent variable would be the amount or number of applications that then we know that students can make between 0 up to 10. So
Yeah.
in that case, 0 would be students who didn't apply. So we could create a submodel for those students to try to analyze what factors or predictors are related to the decision of not applying at all versus how many applications they submitted. So maybe that's a quick example. But
Yeah, I
in
like
that
that.
case, the dependent variable could be number of applications.
Yeah, so it's like, did you decide to even try to go to college? Yes or no? And then how many
Exactly.
places did you apply to if you did?
Yes. And
Yeah,
there we will have two models.
that's exactly right. I like that. Indeed. I would also say your admission scores could go into that category too. So if you decide not to go to college, then you might not take the entrance exams. So then it's like, did you decide to take the exam? Yes or no? And then if you did take it, how well did you do?
Exactly. Yep.
Yeah. So both aspects, like a qualitatively different groups of people who decide or not decide to go, and then how well did you do amongst the subpopulation? Yes, I like that. Thank you. So yeah, I feel like this is very useful. And in homework 4, I'm actually asking you to do something like this on the X side. So if you have a predictor and you want to treat it this way. So did you decide to apply? And if so, how many places did you apply to as a predictor? That would be considered like not a two-part model. I would almost call it a piecewise model. in that case. And it's similar to what you would do for different sections of a growth curve in a longitudinal analysis. So homework 4 has that as part of the story, which I'll delay talking about further until I've opened it to you, since you don't have a chance to look at it yet. But I'm looking for generalization of these concepts. So yes, I feel like hurdles and two-part models are very useful for those sorts of qualitatively different mixing population things. Okay, so I think we've talked about most of that. So in terms of comparing models, like when you're in this world of which count model do I need, I would recommend the following. So whether or not a dispersion scale parameter is needed, so whether or not there's over dispersion, variance more than the mean, that you can answer with a likelihood ratio test. For the Ferris comparison, I would keep the linear predictor the same. So don't change out what predictors are in the model, just focus on what distribution is being used. And to do it most properly, we need a mixture. So the idea of a mixture chi-square. This is for situations in which the new parameter that you're adding to your model, the null hypothesis for it is on the boundary of what it could possibly be. So in this context, the k thing, there's one parameter which I call the scale parameter or the stretchy parameter, that reduces to 0 if it's Poisson. And so the null hypothesis that you would typically test for a parameter is whether it's different than 0. The stretchy parameter that differentiates negative binomial from Poisson can't be negative. Like it's not possible in the way that it's coded. So it can only be positive. So to ask whether the model fits better, whether it's taller, if you have that k thing in, it's not a full degree of freedom that you would spend for it, it's a half essentially, because it's the part where it would be positive. So a mixture chi-square then, degrees of freedom 0 is not a thing. There is no such thing as a chi-square with degrees of freedom 0, so that just makes it literally 0. So this is a very long-winded way of saying cut your p-value in half. That's your take-home message, okay? In this context, if you're adding one parameter and that parameter can't go negative, you can cut your p-value in half, and that's the more proper way to do it. The same thing happens if you're adding a random intercept variance, for instance, in a structural equation model or multi-level model. There's other instances in which this happens too. So chi-square mixture is the idea here. And in this case, cutting it in half is sufficient. When it's more than one parameter, it's not that simple, but in this case, that's fine. The same thing happens in whether or not you need zero inflation. People disagree about this because like the lowest the probability can be of being an extra 0 is 0. So it's the same thing, like it can't go past a certain point. So I've seen people use a likelihood ratio test with a mixture chi-square for this. I think you can also just look at the parameter, and if it's sufficiently small, you probably don't need it. You can compare AIC and BAC always. And in terms of comparing across distributions, you can't do that. So that's the one thing really you can't do, and I wish you could. So for instance, if I have my count variable and reviewer 2 is like, I think you can just use a normal distribution, there's really not an easy way to shut them up. There's not a likelihood ratio test or other kind of comparison that can test normal against count. You have to stay within the same distributional family to do the likelihood ratio tests. The issue is because they're literally on different scales. So if you're fitting a model that were normal residuals, like a normal conditional outcome, the formula for calculating height uses the normal distribution. The formula for calculating height in a count model uses a different distribution. So they're not comparable. This is where the Wong test thing used to be used for this too, to some extent. So I would just look at Pearson chi-square over degrees of freedom in those cases to decide amongst plausible models. I would look to see if the predictions stay within the boundaries. So if you have a predicted count that goes negative, that's a sign that something went awry, that kind of thing. So, I've got some slides at the end here for all the different places where you can find the software across SAS, Stata, and R, and extensions to multivariate models as well. This is just an additional resource. Yeah, I think that's probably good for now. There's one more model that I had done in example 3 just because I thought it was cool, not because you need to know this in your lives, but I liked it, in which you can actually predict individual differences in the stretchy factor. like the K dispersion. You can predict like that as an idea. And so I found a thing in Stata to do it. GNBReg is what it's called. And in this particular data set, we didn't have any indication that that was needed. So I didn't do that model. So then here's the rest of the write-up for what this would look like. So, all right, I think that's all I had wanted to say about counts. Any questions or things that are still confusing or that you want to go back over with respect to count outcomes and their associated distributions? You think of anything? Not at the moment? Okay, fair enough. Then I'm going to shut down one recording